Good morning, mathematicians. Welcome back to another office hour. Hope everyone's doing well. Just gotta wait for chat to pop up. There we go. What to yap about today? Maybe more stuff to do with modules? I don't know. Start ourselves off with Reddit as usual. I haven't yapped about graph theory for a while. I could do that as well. It hasn't been on my mind as much. Why are separable spaces called separable? How do you research for math? Interesting. Oh, good morning, Deepak. Good morning, Deepak. Yeah, I don't know if I want to dive into that question right now. I'm all over the place. Okay. Sorry, I'm out of it. I gotta start yapping. There's a recent talk by Scott Aronson I might like. Scott Aronson. Maybe I should go to YouTube. On YouTube, I'm guessing. Oh, is it this one? How much math is knowable? Yeah, I think that came up in my feed. I just haven't watched it. Yeah. Interesting. Yeah. Okay, I gotta start yapping. Jesus. Gotta start yapping soon. Gotta let the coffee hit, I guess. Oh, what are we gonna get into today? I don't even know. Let's go back and take a look. Probably return to the heck algebras. That's the one thing on my mind right now. But I don't know how much more. Okay, well. Yeah. Let's talk about the heck algebras. So, previously, we had discussed a bunch of things about the representation theory of GLN. So, I talked about how every multi-segment, which is a multi-set of segments, and segments are just ordered intervals of integers or half integers, so this segment would be this ordered set. That these multi-segments, subject to some certain conditions, gave a complete combinatorial classification for the irreducible representations of GLN. And in fact, there was something that I said I was leaving out at the time, that technically you need a little more information than just the multi-segments. But this information that we're missing is actually just the fact that, so we've also talked about this Iwahori heck algebra. And it turns out that the multi-segments I've described for you are exactly the representations that correspond to irreducible representations of the Iwahori-Heck algebra. Actually, we do need non-integer, other non-integers like arbitrary complex numbers as well. But otherwise, yeah, multi segments. But pretty much all the questions you could ask, you can just ask them about integers and half integers. You're working through a proof in Hartshorne, and he mentioned very quickly ind ab x, which led you to read up on ind objects. Really? That's in ind objects are in Hartshorne? Is it just the incompletion of the category of coherent sheaves? Honestly, I don't even know. I've just seen like ind objects come up, and I looked up some definition, and it looked at like some 2 limit. So I don't know. This is something I need to know. I should know. Wow, he talked about ind AB, huh? That's interesting. I didn't know that. Stable infinity category of incoherent sheaves. Okay, it's defined as this isn't like, there's probably other definitions that aren't infinity categories, but probably this is the best one, and we should all learn it. It's when he proves that direct limits commute with cohomology on a Noetherian topological space. Really? Huh. I wonder... Oh, no, I don't think I have a... Oh, let's see if I... Interesting. Let's see if we can pull that up. This is somewhere in chapter 2, I'm guessing. If you know the exact page or whereabouts roughly. 3.2.9. Okay, that's around 206. 3. Oh, were we still in chapter 2 here? Three 3.2.9. Aha. So what does he first mention it? For the general case, we consider the category consisting of all directed systems of objects indexed by A. Interesting. Okay. And says it's an abelian category. Interesting. Yeah, so I guess it's some sort of... Right, yeah, I guess it makes sense. It's some sort of limit completion of the category, I suppose. Huh. Very interesting. Let's see, what does NLab say in ind object is? Well, maybe we should look at the classical category theory ind object. An ind object of category is a formal filtered colimit. Formal means it's taken in the category of presheaves. Category of ind objects is written like this. Yeah, okay, so that sort of tracks with what I said. Huh. Ind categories allow one to handle big things in terms of small things. Ooh, many large categories are actually equivalent to ind categories of small categories. Interesting. What are such examples? Examples. Finite dimensional vector spaces. Oh, okay. That makes sense. Infinite dimensional vector spaces. Hello, morphisms. Good morning. Oh, the category of groups is in the category of finitely generated groups. Okay, that makes sense. That makes sense. Infinite stuff is generated by finitely generated stuff. What's up, Julie? What's up? What is up? Okay, okay. So slightly, we've learned slightly more about Indco this morning so far. So thanks, Nicholas, for the question. Yeah, one of these days. I wish there was a course. I wish I could just take a mini course on Indco. I'm sure there must be lectures. Yeah, there's notes, but I wonder. There's no summer school, hey. Oh, Gatesgory has a set of notes. Oh, this is probably though. Okay, this is Gatesgory 2011 on archive. This is probably like a serious work to develop the theory. Which okay, probably worth reading, but odds are I'm gonna need something a little more overview and lightweight first. There is, of course, the book Gatesgory Rosenblum as well, which I should read. But there's only so many hours in the day. Yeah, okay. I guess I should get back to yapping. The problem is I need to understand infinity categories better. That's always the problem. That's the central problem in all of this. There's just no time. I have research to do that doesn't involve that at all. What can I say? So, speaking of my research and getting back to yapping about that, could I talk about research assistantships and what to expect from them? You're a second-year math major, and you'll be doing an RA over the summer, and you're just curious as to what you can expect. Well, I mean, I did one when I was in undergrad, but, I imagine, like a lot of things, it can vary a lot from place to place and supervisor to supervisor. But I can tell you, well, I guess I technically had two. So the first one I did was very, like, I was expected to be at the university at like 8 or 9 and stay until like 4 or 5. So I was basically expected to put in like 8-hour days with lunch, which, it's not like it was closely monitored, but there was like a particular room. It was just an empty classroom that all of us who were doing RAs there would work in. And so, like, my professor expected that if, she came down, she'd, like, find me in the room or something at some point during the day. So, yeah. And then, yeah, you basically just sit around working on math all day. It was great. Sometimes I would, if it was really nice outside, I would, and I had some stuff I could do with that I didn't need internet access. I'd go, there's this like front lawn of the university, I guess. I would go sit out there and do work like under a tree or something. But yeah, so that's pretty much how that one went, and it was fine. It was good, yeah. Then the second one I did was definitely a lot more free in the sense I didn't have to be anywhere at any specific times. I just met with my supervisor regularly, sometimes in coffee shops, most often in coffee shops actually, and we would just chat about what I'd been working on. And it was like totally up to me how many hours a day I put into it, um, and how much I got done really. So yeah, that was nice. I wonder if I would have gotten more done had I had to be in the building at a fixed time. Good morning, Edit Smith. So it's great. I would say, I mean, yeah, work. I don't know. I was gonna say work as hard as possible. Go hard on it. That's true. I do believe that. But also, like, I don't know. Did I work hard? No, I was just kind of obsessed with math. So I don't know. Maybe if you feel like you're working really hard, like also don't sweat it. I mean, our research assistantships don't always like produce publishable results. So focus more on learning. Uh, yeah, make sure you learn a lot. Today is Thursday, but I'm done with my math help center hours. It's the spring semester now, so I'm free. I'm free to stream 24/7. I mean, not 24/7. 7 days a week. Uh, um, yeah, it would be crazy. I could do like a marathon stream one day, maybe like a 24-hour stream where I just like solve exercises live from Hartshorn or something, like raise money for a charity or something like that. That'd be fun. Actually, that'd be torturous. I'm too old to do stuff like that now. But yeah. Although speaking of, on this weekend, I may not be streaming Saturday or Sunday, so I'm gonna be in a cabin in the woods. Actually, a giant barn in the mountains. So yeah, mouthathon or something. Yeah, yeah. Maybe one of these days, some sort of thing. Try and speed run. Actually, I was joking with someone. About uh, trying to speed run all of mathematics, do a live stream and start from like the basics of ZFC and try and build everything up. It'd be a nightmare. What is a good idea to improve at proofwriting? Yeah, you know what? Here's the thing. I yap all the time about all sorts of stuff and all sorts of advice. And so I'm going to tell you what I think is true, but I realize I have like no evidence for some of the things that I'm saying. It's like it's not like I've conducted double blind randomized control peer reviewed trials. You know, so actually, some of these things I'm like, I don't know. Is what I'm saying even true? Or does it just work for me? Is that even how I improved? But here's what I think is true. I think I do think it's true that there's really fundamentally there's a lot of things you can do, but fundamentally there's only two things you can do, and you need to do them both. You need to read proofs and you need to write proofs. So you just got to practice those two things. Well, of course, that's not super helpful information. You probably understood that at some level already. But, well, certainly when it comes to writing, I mean, also writing with feedback. Because, of course, if you just keep writing slop and tossing it into the void, that's not really going to help you. Writing with feedback. So how do you get feedback? Well, of course, there's your courses. But you probably want to do good on those, so you don't want to just rely on feedback from the TA marking your courses. Which, by the way, your TA or your professor doesn't always have time to give you very detailed answers, and sometimes students complain about this. I try to give a couple sentences if possible on each point, but make use of office hours. To go and get more details about the nature of your mistakes and how to improve. Okay, well, it's summer. Maybe you don't have access to professors. Maybe you're teaching yourself. Maybe, I don't know, maybe you're not in university right now or something. Who knows? Um, so you still need to get feedback, either from friends, so people, um, people that you study with. It could be just people online. There's like, I don't know, Discords and Reddits and stuff for more like elementary, like learning math things. You could also get a tutor. Of course, that option costs money, and the other things are free. One of the other things, though, so that's all to do with writing. When it comes to reading, make sure that you are actively reading your textbook. So what I mean by that is like you physically have your textbook with you, and then as you're reading your textbook, like your notebook is open, and you've got your pen out, and you're like copying a proof down, and maybe copying a proof down as you read it. And then maybe see if you can improve upon the proof, right? Because, maybe this is like a textbook that was like written quickly, or it was written with the idea to intentionally leave some details for you to fill in. So, pay attention when you're writing these proofs, right? If there's some step that the author just explains in one sentence and they're like, oh, it's clear, and you didn't find it so clear, just basically copy their proof. I mean, essentially plagiarize. I'm not saying to do this on your homework, or don't plagiarize to put on a blog or something, but like literally plagiarize the proof. But then in well, maybe even then, even if it's just for yourself, I would say still try and put it in your own words. But the point I'm trying to get at is add those extra details in there. That's what I would suggest. So those are things I'd suggest. Is it just for you? But brute force usually works really good. Like write the proof down 5 to 10 times, even if you don't understand. Eventually you'll get it. Yeah, I don't know. I don't know if that would help me get it. But certainly I did make myself memorize a bunch of proofs for some courses, just because I was like, okay, well, I know that either these theorems are going to be on the final, or proofs requiring similar tools, and so I did just memorize some proofs. Yeah. Yeah, if it works for you, I mean, that's the other thing too. You got to figure out what works for you. Yeah, people have different ways of learning, processing information. So, well, just you wonder if ever checked out Friedel's algebraic topology notes? No. Even going a bit into Morse theory. Oh, interesting. Yeah, Morse theory is something. Yeah, there's always just too much to learn. Like it would be great to understand Morse theory more. But because it does touch on my work. There's a stuff in my research called vanishing cycles, nearby cycles and vanishing cycles, and I use an algebraic geometry definition of this thing, which is all in terms of like sheaves and stuff, but there's also an analytic definition of these things, and they're supposed to somehow agree, and somehow it has something to do with computing Morse groups. But I don't understand that. Let's take a look. Actually, I should look at the. I'm gonna look at this seven page notes. Those look good. Does Morse theory involve dots and dashes? It really should. It really should. It really should. Yeah, I wonder what the legality is if I just like if I did streams where I just like read a textbook and worked through examples, you know? Like what if I started a live stream series where like a couple nights a week I just open up a Luffy and I just read it from like cover to cover, peppered with examples. Jesus Christ, this document is 3,000 pages? Oh my god. Yeah, you weren't lying when you said it was comprehensive. Oh my god. Wow, starts right from general topology. Oh. Oh lord. Yeah, I don't know. This is too big. Even as a PDF, it's too big. I'm never gonna read this. Somehow it's psychologically I can feel the weight of this in my head. Wow. Yeah. I mean, hey, it's good to have everything all in one place, I suppose. But yikes. Doesn't seem long enough. Yeah, I mean, yeah, what's how long's I have a copy of higher topos theory. How long is that? Oh, it's not even 2,000 pages. Higher topos theory isn't even 2,000 pages. Come on. Yeah. Well, I don't know. Yeah, I'm never. I opened it once. I'm never gonna open that document again. I think. I will. Yeah. That is where is it? It's in chat here. Friedel's algebraic topology notes. Very comprehensive. Yeah. This comment up here from Sabi. Uh, Higher Topo series is like 900. Yeah. Okay. Chump numbers. We saw a book that was almost 2K. If I was that person who wrote that book, what was it? The book we just closed that was like 29 something. Come on, I mean, just write a few extra pages, break that 3K mark. What are you doing? Math problem solved, Joe. Do I know anything about getting a PhD in Canada? I know everything about getting a PhD in Canada, because I am getting a PhD in Canada. Well, no, I probably don't know everything. I'm definitely missing the forest for the trees, I'm sure. But yeah, you got questions about doing your PhD in Canada, uh, let me know, eh? I could tell you all about it. They make you put maple syrup in your coffee every morning. It's a national law. Um, while I'm waiting for that question to trickle in, I'll maybe yap slightly more chaotically whiplash back to representation theory. So we had talked a little bit about the Heck algebra, the Iwahori Heck algebra for GL2. We also talked about some of the representations. So remember the total length of the multisegment has to equal the n in your GLN. So all of our multi-segments can either be, well, it would have to be a single segment. So it would have to be two numbers, a and a plus 1. Or it would have to be two singleton segments. So our multi-segment would either just be a single segment, or we would have two singleton segments, say A and B. What the heck is that? What the heck is what? The Heck algebra? I've yapped extensively on it the the last few streams if you stroll through some recent live streams. But maybe I'll say something moderately comprehensible about it in a second to get you caught up. But for now, a multi-segment is just a combinatorial gadget. So really, whatever the hell a multi-segment is, we're thinking about multi-segments of length 2, and so that either contains a single thing, delta, which is just an ordered pair of numbers, really, that differ by 1, or there's a multi-segment which are just 2 singletons of numbers. And the point is that these are supposed to like combinatorially classify the irreducible representation. So these multi-segments, by some mysterious process, give us a labeling system for the irreducible representations of GL2 over a p-adic field. Well, and we add some like words about topology and stuff. And so, well, we saw one example where we had this short exact sequence, which didn't become a direct sum, which was the... am I writing this the wrong way? I think I'm writing this the wrong way. I am writing this. Wait. No, this is the right way. Always get myself confused here. So we had some short exact sequence. Didn't break up as a direct sum. This is the trivial representation, and the way that we wrote the multi-segment corresponding to this is just the 2 singletons 1/2 and minus 1/2 as a multi-segment, and the multi-segment corresponding to this thing over here, which is an infinite dimensional irreducible representation, was this segment from minus 1/2 to positive 1/2, so just this singleton segment. And we had this general rule also that if you have a multi-segment, you were able to create a new multi-segment related to it. And what is the rule for doing that said that if you had 2 segments, and if they were linked, which means, so if we sort of draw a picture of these segments, so that means there's some, either there's some overlap, or they just differ by 1. There's just a difference of 1 between their endpoints. Then you could form a new multi-segment, which contains you remove those 2 segments and you replace them with their union and intersection. So in this picture we have for GLN, there's our segments. So of course, if you have a single segment, there's no way that this can be linked. There's only one segment, so you can't have a pair of linked segments. What would it mean for these 2 segments to be linked? Well, and we also had the condition, one can't be a subset of the other, so we don't say they're linked in that case. So we have this other condition. Well, how could they be linked? Well, it's if and only if either A is B plus 1, and then we could say or B is A plus 1, but this is just a multi-set, so it doesn't it's sort of without loss of generality we can flip them, right? So either this leads us to well, here's the one other key point. We also had this fact that I defined these things called standard representations. It was some irreducible representation, and we had a theorem that an irreducible representation pi b shows up in SQA if and only if b is less than or equal to a. So what that means is if b is obtained from a by some sequence of these multi-segment operations. So let's apply this now to GL2. So we find that if we look at these segments, A and B, and we suppose that A is not equal to B plus or minus 1, so they don't differ by exactly 1, well then, and let me call this, or maybe these are, I'm using A for multi-segments, and then these are, there's supposed to be numbers in here, so I don't know, maybe, what do I want to call these? M and N? I don't really like that notation, but okay. So let's say I've got this pair of numbers here, and M and N don't differ by 1, then whatever this representation is, well, there's no, I can't obtain any multi-segments from A. And so that means that the only representation that lives in this thing is, in fact, is the irreducible attached to A. And, okay, it could live in there more than once, but one other theorem I'm just going to use without proving is the fact that that one only lives in there exactly once. So in other words, this representation is irreducible. And remember that the way that we cooked up this representation. So if I decide to order this in such a way so M is strictly greater than N, the way that this representation was cooked up was that we took the this, I used this notation new for the character. So new box, new M, box, new N. This was the character of the torus of 2 by 2. So of the, diagonal matrices in GL2, T1, T2. And this spit out the character where we take the p-adic norm of T1 raised to the power of M and multiply that by the p-adic norm of T2 raised to the power of N. And then we perform parabolic induction. So, okay, some fancy words here, but it's basically the exact same idea as induction for representations of finite groups. Somehow I feel like I should stop yapping about my research, because I feel like chat always grinds to a halt when I do. Everyone's just so memorized or cooked by what I'm saying that the questions stop. But maybe it's good, because then I get some thoughts out about my research in between questions. I don't know. So right. So now we have an entire class of irreducible representations. We've looked at the case when these when we have multi-segments exactly of length 2 with 2 singletons. Good morning, William. And we so exactly get this class of irreducible representations. I think I also called these things QA. That's what I was calling them before. Sorry, that pi might be confusing for people who go back and look at other ones. Right? So okay, now we have some sort of class of irreducible representations that we get from inducing things from the center. And I'm going to connect this back to Heck algebras in a moment, I promise, but perhaps we'll that'll have to wait for tomorrow. So what about the other case? What about the case where I have two singleton segments that differ by exactly 1? Well, now these are linked, and so I can create the segment. I can create the segment which takes the union of these two and their intersection, which is just the empty set, so I ignore it. So the only other possibility we see is that, so again, for this. I've used A. I've used A again in the wrong spot. I don't want to use it there. I'm using A for my segments. Call this A, call this B. M, I guess. Right, so the only other possibility is if so again the way that we build SQA is exactly the same, right? We still just induce these characters with the exponents in decreasing order, except now we find that this does have to be reducible. And okay, again, I'm not exactly proving this part of the claim, but it'll turn out that this thing always has length exactly 2. So oh, wait a second, am I doing something silly? Yeah, so this will be SQA. This induced thing here. So it'll be induced from this norm character. It will it has its unique irreducible quotient, which we would call QA, and it's got this whatever it turns out, whatever QB is, we get a short exact sequence. So QB only shows up once in this representation. They both show up exactly once in this thing. And then also we know that so what is SQB? Well, by the same reasoning, there's no multi-segments below this. So this one is irreducible. And so we can basically see this as a way of cooking up QB. Actually, we can be more explicit about what this QA looks like. So now we got to be careful because I'm writing things in a slightly different order. So if I scroll up here for the case minus 1/2 to positive 1/2, see here it was in. So notice the trivial representation is the kernel, and what we call the Steinberg representation is the quotient. If I flip the order, interesting. There's reasons for this. There's like several cool explanations to do with like interesting operations on p-adic groups. But if I swap the order, now the Steinberg representation is the sub, and the trivial representation is the quotient. And this is maybe, Q of 1/2 minus 1/2, and this is Q of the singleton, the single segment here, and this is SQ of let me just call this A. Right? So now, however, we can, what I'll do is I will, it turns out that tensor products are an exact functor, define an exact functor in the category of representations. And so I can tensor everything by mu to the m, and okay, this is very sloppily written, but I still get an exact sequence. And now the key is this term in the middle. What this becomes is this term basically distributes into both of these. So this becomes the term ind m plus 1/2 tensor m minus 1/2, right? And in other words, if I define n to be m minus 1/2, then this becomes int m n plus 1 n. Okay, so you figured out a question, not exactly related to Canada, but what books would I recommend after Attia, MacDonald, and Dummett and Foote? You have Hartshorne, but honestly don't want to go in unprepared. Yeah, Edith Smith is right about Eisenbud, I guess. But actually, I mean, if you already read Attia, MacDonald, and Dummett and Foote with a solid understanding, then you can absolutely start reading Hartshorne, if that's what you're heading towards, is algebraic geometry. So yeah, absolutely. Like, I don't like Eisenbud's great, but I don't know if you need to go in. I don't know if you need to go in to something else in between. Like, I would just, at this point, I would jump right into Hartshorne, and then as you'll probably encounter certain things you're like, oh, I don't know what that is, and then you can go and backfill. Yeah, I think you're about as prepared as you need to be, most likely. Yeah, if you work through Attia, MacDonald and know topology, you're prepared enough. Yeah, exactly. And no topology, I mean, you don't even need to know that much crazy topology, right? Like basic point set stuff. Yeah. So one of the punchlines. So notice we have int new n1, new n, and basically because we can choose m to be any complex number, this means that we can really choose n to be any such complex number. And int of this thing, well, this is exactly what we would have called SQ for the multi-segment of the two singletons, n plus 1 and n, right? And this is exactly the case that we were missing. And so that must mean, because this thing has a unique irreducible quotient, that must mean that its unique irreducible quotient is just the trivial representation, tensor the character. I've done something a little, here's a place where okay, we just write this for notational convenience. I've said something a little weird, right? Because, of course, when I write, say, new m tensor this, or new m tensor this, I mean, this is weird, right? Because new m, this is just a character of, say, the underlying p-adic field, right? Like, new m of a p-adic number, say, x, is just the p-adic absolute value of x to the power of m. But this is supposed to be a representation of GL2. So what I mean when I'm writing something like this or like this is actually the composition of this character and the determinant. So what I mean in general, if I write new m as a character for GLN, what I really mean is that new m takes a matrix G. That first you apply the determinant to G, then you apply the p-adic absolute value, and then you put that to the power m. So there's a little bit of notational mishap happening. So whenever I write, so when I'm writing it here, new 1/2, I literally mean like the character, just the norm character. But when I write it over here, I mean the determinant composed with norm character. But so the punchline is that our int new n plus 1 new n is exactly SQ of n plus 1 n, and maybe just to be extra clear, I'll write this as new. What should I write this as? New. What did I multiply by to get there? Right. So how do I get? Let me see. How do I get m back out of this? Right. So if this is n, and this is sorry, this is n. This is n plus 1. I guess. I guess we have what? So n plus 1 plus n is equal to 2m. And so this is 2n plus 1 equal to 2m. And so this means that n would have to be 2m minus 1 over 2. Or rather, m is 2n plus 1 over 2. Right. So going down here, this would be 2n plus 1 over 2. Composed with the determinant character. This has to be the irreducible representation attached to this multi-segment. And whatever this Steinberg representation is, just twisting it by this character. So again, I do mean composed with the determinant here. That has to be the irreducible representation attached to this multi-segment. And so this gives us, now putting all of these features together, we've now pretty much obtained a classification of all irreducible representations, well, that belong to the principal block. So that's just a fancy way to say that should be captured by the Iwahori-Hecke algebra. It's exactly these together with these irreducible representations where m is not equal to plus or minus n. Yeah. Sorry, is not equal to n plus or minus 1. And this gives us a complete classification of all of these representations. And, well, these sort of infinite dimensional ones, that's maybe kind of mysterious. To get a grip on them. These ones are pretty easy, right? Because this is just like characters. So we understand characters. Those are one-dimensional. But these are, the other ones are infinite dimensional. And maybe at the moment now, so are these. So here's where the Iwahori, there's a lot of reasons why it's useful, but it can come into play to give us a more down-to-earth understanding of these things. Because one of the words, which I think I did just briefly touch upon in the, so maybe I'll put rep. I'll put a little circ here to remind us we're looking at a subcategory, not the entire category. One of the words that we add over here, just some sort of topological condition we put on our modules, is that they're admissible. So that means that what that translates into is when we go over to take the corresponding module, it will be finite dimensional, finitely generated module. So that means that even though the Steinberg representation is infinite dimensional, when we go over to this perspective on modules, we'll get some finite dimensional thing, and maybe we can get a grip on it. So we can try and use our understanding in order to think about these irreducible think about these irreducible representations in terms of modules. So we've got these generators and relations as well. And so we can already even start to think in a purely module theoretic way. We could even think, well, what are the symbol? I'm gonna try and create finite dimensional irreducible modules. That basically just means that everything in my ring should be acting like a scalar. So that already seems like I have, for t there should be two options. Either it acts by -1 or it acts by q. And then probably the other relations that I have, which I'm not going to write all of them out now. But those should be, we should basically be forced into some choices of scalar beyond those two. So how are we going to make these computations? Well, I might have to. My coffee's almost done, so I'm going to leave it for today. But I'll just remind you that the way that we compute how this works. So if we're given a representation of GLN, the corresponding module, remember, one interpretation, well, although we have these nice generators and relations, one interpretation of the Iwahori-Heck algebra is in terms of these functions defined in our group G. And so we define the corresponding action of the module to just be the following integration. Right? And so we're going to use this, we're going to use our expression in terms of the, in a previous live stream, I talked about a basis for these functions, and we can use that basis to explicitly determine how our module is going to behave. So I think that's going to do it for today. Thanks everyone for joining me. Time to go prove some theorems. And I have my freedom. My marking's all done, so I really can spend the rest of my day proving theorems. I hope the same goes for you.